Hello PU2 warriors, welcome to the crash course. Today I am going to discuss a very important high weightage chapter for your PU2, which is electric charges and fields. The total number of questions that might come from this chapter is actually 11, and we will also show you the previous year analysis that we have done. So if you see the previous last 5 years analysis from the chapter, you will see that the questions or the topics that is coming from these chapters are based on Coulomb's law. It came 4 times in last 5 years. Electric field applications, mainly numericals, came 3 times in last 5 years. Properties of electric field lines, it came 4 times, very important question. Gauss's law came twice. Electric field due to a long straight wire, the derivation came only once, and electric field due to a spherical shell based numerical question came in only once. In 2025 there was a question based on the concept of electric field due to a charged spherical shell, but that was a numerical question. So let us start with the chapter. So we know that there are 2 types of charge present in nature. What are those 2 types of charge? One charge is positive charge and another charge is negative charge, right? Now what else? We also know that like charges attract each other. Is it? No. Like charges repel each other. Okay, so like objects repel each other, like charges repel each other, and unlike charges attract each other. So for example, positive charge will repel another positive charge, negative charge will repel another negative charge, and opposite charge means positive and negative, they will attract. So positive positive, negative negative, they will repel each other, whereas positive negative or negative positive, they will attract each other. This is the basic nature of charges. Now only electrons can be added or removed to charge any object. So for example, if I want to charge an object, only electron you can add or remove. Now we know that electrons are negatively charged object. Okay, so that's why when you add electron, the object becomes negatively charged, right? Because electrons are already negative. So if you add extra electron, then the object which was initially neutral, it will become negatively charged. For example, I have a suppose we have a neutral object. In a neutral object, number of positive charges and negative charges are equal, right? So if you want to charge this object, what you have to do? You have to add some extra electron to this. So when you add some extra electron, the object becomes negatively charged, right? And if you remove the electrons, whatever already present in this object, neutral object, okay, so if you remove the electron, then it becomes positively charged. Why? Because this charge is removed. So once you remove this charge, there is an imbalance of charge. So because of the imbalance of the charge, the object becomes positively charged, right? So only electrons can be added or removed, and by adding or removing electrons, you can make an object negatively or positively charged, right? What else? So now how can we detect that if an object is charged or not? So for that, gold leaf electroscope is a measuring device which can measure that if the object is charged or not, and it is a very simple design, and I hope you have studied about it in your lower classes. Not super important, but just for information that gold leaf electroscope can be used to determine the presence of charge. Now let's continue. The SI unit of charge is Coulomb, right? And its dimension is ampere, A into T. Okay, A into T is the dimension of charge, right? Now let's move on. Okay, next is conductors and insulators. So based on how these electrons that we are talking about can move through a material, we divide an object into 3 different categories: conductors and insulators. We will study in this chapter. There is a third category, semiconductors. We will study them in a later chapter. Okay, so conductors are charges can freely move through them. So basically electrons, charges means electrons. The electrons can freely move through certain objects. Those objects are called conductors. Conductor has a lot of free electrons to carry electricity. This is a major thing. In current electricity chapter, we will discuss more about this property. Metals, graphite is a non-metal but still is a good conductor. So these are few examples of good conductors. Here you can see copper, aluminium, silver, iron, they are all good conductors. Charges given to a conductor always lies on the surface of the conductor. This is very important point to remember, because a lot of time you will see questions based on this property, that if you add some excess charge to a conductor, what happens? This excess charge always stays on the surface of the conductor. So whatever, maybe you have removed some electrons, maybe you have added some electrons, so whatever is the extra charge means the inside part will always be neutral. Inside part will always be neutral, but whatever extra charge that you have given to the conductor, that charge will always be on the surface. For example, if you take some wooden piece and put it into the water, the wooden piece will always float in the water. So similarly, you can consider the conductor like water and charges like the wooden piece. So those wooden piece will always lie on the surface of the water. Similarly, charges here will always stay on the surface of the conductor. Clear? Next, we are discussing about insulators. Charges cannot flow through them. They have almost zero free electrons. So for example, plastic, paper, non-metals, they are generally considered insulators. Obviously there are few exceptions. For example, graphite is one exception. Even though graphite is a allotrope of carbon, but it still can carry current, right? So here there is a picture, nice beautiful picture. You have seen that we have electric post which actually helps us to carry the current from the source to some place. Right now, how these posts, even though it is made up of metal or wood, does not matter. Why when you touch a electric post, you does not get electrocuted naturally? Yes, they are not safe to touch, because in case of rainy season or some leakage, they may still get charged and you still get electrocuted, but in general you don't get electrocuted if you touch the electric pole or lamp post. Why so? Because they are disconnected at the lamp post using these insulators. Okay, so these insulators actually disconnect the wire when it is coming to the lamp post. And there are some hanging wires. These hanging wires actually carry the current from this end to this end. So near the post, this is disconnected through insulators, but these hanging wires actually connect the wires and they carry the current. So in some case, if this hanging wire get in touch with the lamp post, then you still get electrocuted. So be aware of that. Don't touch the lamp post if it is not needed, right? Clear? Now, basic properties of electric charges. We know that there are three basic properties. First is charges are additive in nature. What is the meaning of that? Charges can be added algebraically. Algebraically means just like scalar numbers. So 2 plus 2 is 4 for charges. Okay, we know that in case of vectors, 2 plus 2 may not be 4. In some cases it can be 0 also if the vectors are in the opposite direction, right? But in case of charges, it is not so. It will always be you can always add the charges like a normal number. So if you add say q with minus 2q and plus 3q, then the total charge will be 2q. So whatever sign of the charge, you have to consider the sign of the charge, and then you can add them just like normal algebraic numbers. Charge is a scalar quantity. Obviously, because charge is a scalar quantity, you can add them just like normal numbers. The next part is charges are conserved. Now you have to be very careful about this statement. Charges are conserved for an isolated system. Okay, it's very important to remember. Charges is not conserved for any system. Charges are conserved only for isolated system. If the system is open, then charges are not conserved. Isolated system means, suppose we have a system which is not interacting with the surrounding. okay, or which is basically closed system, which does not have which is not exchanging anything with outside, then it is called a closed system or an isolated system. For example, if you all sit inside the classroom, then the classroom can be considered as an isolated system if the doors, windows, everything is locked, right? So in that case you can consider the classroom to be an isolated system. But if you open the door when during the recess period, you all go out of the classroom, then the classroom is no longer an isolated system, it is a open system. Okay, so isolated system means when it is not interacting with outside. So if I say that the total number of students in your class is 30 in a particular day, when the doors are closed, no student can go out of the class, then total number of students in the class will remain 30 as long as the doors are closed. But if the doors are open, some student went for the washroom, some student are playing in the playground, then total number of students will not remain 30, right? Very basic and easy example. So this is why we say that charges are conserved for isolated system. Be careful, I have seen students making mistakes. They think that charge is conserved for any system. It is not, it is only conserved for isolated system. It is not possible to create or destroy net charge carried by any isolated system, although the charge carrying particles may be created and destroyed. So there is a process of creating charge carrying particles. So from energy we can create electron and positron pair. So that is possible, but total number of charge in an object will still be same. Okay, even though total number of charged particle can be different, but total amount of charge in that object will remain constant if it is an isolated system. And last point is very, very interesting, and based on this point we often see a lot of questions coming in your KCET, maybe sometimes in your PU board exam as well. So this is a very, very important property, that charges are quantized. What is the meaning of quantization? All free charges are integral multiples of a basic charge that is denoted by E. E is basically charge of an electron. Okay, and Q equals to NE. Here N is an integer number. What is the meaning of integer number? Plus 1, plus 2, 0, they are all called integers. Plus 1 or minus 1, plus 2 or minus 2, okay, plus minus 1 basically, plus minus 2, 0. So they are all called integers. 1.1, 1.5, 3.2, they are not integers. Okay, so they are decimal numbers, but they are not integer numbers. Integer number means basically you can say in a sense both way of whole numbers. Okay, so there is no decimal involved, it is a complete plus 1 only, there is no decimal number involved. So they are called integers. Okay, and here E is basically charge of an electron, and its magnitude is approximately 1.6 into 10 to the power of minus 19 coulomb. If any other value you have to use, that value will be provided in the question. If the value is not provided, you have to take this value 1.6 into 10 to the power of minus 19. Now let us understand this quantization property in a little bit detail. Okay, so what is that? Suppose you went to a milk shop, okay, and you want to buy some milk. So you said, I want 2 drops of milk or 1 glass full of milk. Will the milk seller give you 1 glass full of milk? No. So you have to buy either the whole packet, or you cannot buy anything at all. So the milk seller will give you the minimum smallest possible milk packet that they have with them. Okay, suppose you need 1 glass, but in this packet suppose 2 glass milk is there, so you have to buy the entire packet, right? So that is how the electrons also behave. The charges cannot be taken as half of electron or 1/4 of electron. Either you take complete electron or you take nothing. Okay, so here we have either one packet or 2 packet or 3 packet. So whenever we say the milk you need, suppose you are making some sweet at home and your mother said, hey beta, please bring me 2 packets of milk, right? 2 packets of milk or 1 liter of milk or 5 liter of milk, like that, right? Suppose this packet represents half a liter of milk. So if you say 1.5 liter, you need 3 packets of milk, right? You cannot bring 1.44 liter of milk, right? So it has to be the integer multiple of half liter, right? So this is how the system for charges work. So it will be always integer multiple of basic charge, which is called charge of an electron. So basic integer means, again I am reiterating that the integer means 0, plus minus 1, plus minus 2, they are called integers. So it is not possible for an object to have 1.5 of E. Okay, now let's solve one question. A body has a charge of minus 3.2 microcoulomb. The number of excess electron it has. This is from KCET 2024. Don't worry, this kind of question can come in Comet K as well. So body has a charge of minus 3.2 microcoulomb. So total charge is given here, minus 3.2 microcoulomb. Now question says that the number of excess electron it has. So if you consider this term excess, that basically means that the sign of the charge is negative. So negative means extra electrons, positive means less electron, right? So electron deficiency, you can say. Because the charge is negative, so it must have excess electron. Now what is the meaning of microcoulomb? Micro means 10 to the power of minus 6. Okay, so this is the charge of the object. Now we know that from the quantization principle, Q can be written as N into E. Now while applying this formula, you don't need to consider the sign of the charge. Okay, you can take the modulus of the charge, right? And you have to calculate this N. Basically that is the problem. Okay, why we are considering the magnitude? Because it is only about talking about excess electron or deficiency of electron. So in that case, basically it is understood, it is basically talking about the sign of the charge. Okay, so 3.2 into 10 to the power of minus 6 equals to N into what is the charge of an electron? It is 1.6 into 10 to the power of minus 19, right? So you can cancel that. So it will be 2, so it will N will be 2 into 10 to the power of minus 6 divided by 10 to the power of minus 19, which is equals to 2 into 10 to the power of 13, right? So 2 into 10 to the power of 13 is the number of electrons. So correct answer is option C. Now if you see, this is a integer number, because 10 to the power of 13 means there will be 13 zeros after 2. So 13 zeros after 2 is still possible and it is a integer number. But in case it is minus, suppose you solved one question and you found that 10 to the power value is minus, then that charge is not possible, because if you say 10 to the power of minus 1, that means 2 divided by 10, that is a fractional number, not a whole number. So in that case, that charge is not possible. Okay, now let's move on to Coulomb's law. So what is Coulomb's law? Before going into Coulomb's law, you have to understand the basis of Coulomb's law. So Coulomb's law basically talks about point charges. Okay, the size of the charged object is smaller compared to the distance, then that charge is called a point object, or the object is called point object, or the charge is called point charge. So if the size of the object is smaller compared to the distance, then that object is called point object. Now you have to remember that Coulomb's law is only applicable for point objects. It is not applicable for any extended object. Okay, that is one of the drawback of Coulomb's law. Now what is the statement of Coulomb's law? Let us understand. Coulomb's law is basically talking about force. So the force acting between 2 point charge is directly proportional to the product of the magnitude of the charges and it is inversely proportional to the square of the distance between the charges. So what is the meaning of that? So when you keep two charges near to each other, so either they will attract or they will repel, right? We have learned that in our first slide, that two similar charges repel each other, opposite charges attract each other. So basically attraction and repulsion means they are basically applying force on each other. Now you have to measure that force. For measuring that force, Coulomb's law is basically the law which helps you to measure the force that is acting between two charges. Now it says that it is directly proportional to the product of the charges. So suppose one has 1 coulomb charge, another one has 2 coulomb charge. So product of the charge means 1 coulomb times 2 coulomb, that is 2. Right? Now it is talking about magnitude. Why magnitude? Because it can either attract, it can repel. So if they are basically if the product is negative, then they are attracting each other. If the product is positive, then they are repelling each other. So that's interpretation we can do on later time. But for now you have to understand that the magnitude of the force is basically dependent on the magnitude of the charges. Okay, sign is not super important. So sign is helpful for understanding the direction, otherwise it is not super important. And importantly, it is inversely proportional to the square of the distance. So inversely proportional means if you increase the distance by 2 times, the force decreases by 4 times. Okay, so there is a direct proportionality, there is an inverse proportionality. Inverse proportionality means if you increase one term, then that quantity decreases. That's called inversely proportional. And square means if you whatever distance you are increasing, it is decreasing by square of that term. Okay, now mathematically you can write that force. Obviously that force acts along the line joining the charges. So force, what is basically direction is always along the line joining the charges. It can be in this direction, it can be in this direction, okay, based on the magnitude of the sign of the charges, but it cannot be in some direction. It cannot be in this direction. Okay, it always be along the line joining the charges, not any other arbitrary direction. Now let's move on. So Q1 and Q2, two charges, they are basically separated here by a small distance r, right? Now let's continue. So if you write the Coulomb's law in a mathematical formula, then the force between two charges is given by K Q1 Q2 divided by r square. Here K is basically given by 1 by 4 pi epsilon naught, and this entire term as a whole is called Coulomb's constant. Its exact value is around 9 into 10 to the power of 9 Newton meter square per Coulomb square. The unit can also be important. The value we all know. Now here the epsilon naught is called permittivity of free space or vacuum. Okay, how much free space allows, and it is a constant again, and its value is 8.854 into 10 to the power of minus 12 Coulomb square Newton inverse meters to the power minus 2. Now for all practical purposes you can consider this number to be 9 into 10 to the power of minus 12 as well. Okay, so that's how you can proceed. Now for medium of dielectric constant K, the effective distance in vacuum will be r root K. So what is the meaning of that? Suppose you have two charges Q1 Q2 placed in vacuum, then the force is given by this formula. Okay, now if you have the same two charges Q1 Q2, the distance is also same, but instead of having vacuum, this Coulomb's law is basically when there is vacuum between the charges, right? But if you put them inside a dielectric medium means suppose you have water can be considered a dielectric medium. So if you take these two charges and if you put them inside water, then what will happen to the force between them? Okay, so dielectric, it depends on the dielectric constant of the medium. It's generally represented by capital K. It is also called relative permittivity. Okay, now if the dielectric constant of the medium is given by K, then the force can be written directly as Coulomb's constant, okay, Q1 Q2 divided by root over of capital K into R whole square. Okay, so this is the basic formula if you put the entire system into the dielectric medium. Now in case of JEE, there can be some questions where part of it is put into the water, part of it is put into the dielectric medium, but in KCET this formula is sufficient. You don't need to go beyond this formula. Okay, and you can write this, if you are confused, you can write this as 4 pi epsilon naught. Everything will remain same, only the distance will be changed when you calculate the force. Okay, so this formula, based on this formula, we have seen some questions came in the past. Now next is electric field. So electric field is basically talking about Coulomb's law, talking about two charges, right? Minimum two charges are present. If more than two charges are present, you have to apply superposition principle to find the force. That is a little bit complicated part. But what about one single charge? So two charges, fine, we have Coulomb's law. But when we have only one charge, then what? Is there any effect of the charge at some distance? Yes. So even if there is only one charge is present, the effect of the charge can be measured at a distance. Okay, and that effect is basically named as electric field. So electric field is basically effect of some charge. Now electric field can be generated using different methods. For example, a current carrying charge, okay, a moving magnetic field. So there are different ways to produce electric field. We will discuss that in future, but for now, for this chapter, electric field is basically produced by a static charge. One more thing, Coulomb's law is valid for static charges. It is not valid for moving charges, especially in the speed of light, okay, which is called relativistic physics. When everything starts moving at the speed of light, that becomes something different, the physics becomes different. Coulomb's law is not valid in that case, so you have to remember that as well. So electric field is basically when a static charge is present and you want to measure its effect at certain distance. Okay, so that term is called electric field, and electric field is given by this formula 1 by 4 pi epsilon naught Q by R square R cap. What is the meaning of R cap? R cap represents a unit vector. In case the charge is positive, then R cap will be away. In case the charge is negative, R cap will be towards the charge. So for positive charge, electric field is away. For a negative charge, electric field is towards. So these are the fundamental things that you have to remember about electric field. So electric field is a vector quantity. Okay, it is outward for positive charge, it is inward for negative charge. The electric field due to a charge Q at a point in space may be defined as the force that a unit positive charge would experience if placed at that point. So if you place a unit positive test charge, unit positive means +1. Okay, so if you place a unit positive charge, one Coulomb charge, basically. So if you place a 1 Coulomb charge at this point, whatever force is experienced by this 1 Coulomb charge, that is the electric field at this particular point. Alternatively, if a charge Q is kept inside the electric field E, then the force experienced by it is given by F is equal to Q into E. So what is the meaning of that? Suppose we have an electric field. The source of this electric field is unknown. It can be anything. We have a known electric field. We know the electric field has a value at some point is E. Okay. Now if you place a charge at this point, the charge is Q. The charge is Q. So this charge will experience a force. What is the force that is experienced by this charge? That force experienced by this charge is given by Q into E. Clear? Basic formula. This is also, even though this is very simple but super important formula. We will see that in later half. Next is a few points that you have to remember about electric field. The electric field due to a system of charge exists at every point in three-dimensional space. for a positive charge, the electric field would be directed radially outward from the charge. I already mentioned that. For a negative charge, the electric field vector at each point points radially inward. Theoretically, the electric field exists from the charge till infinity. Practicality, it is not, because it dissipates because of the presence of other charge. So if it is, suppose you have a completely empty space, and if you have a small charge placed at some point, in that empty space each and every point will have the effect of that charge. But because our universe filled up with different materials, different objects, we do not feel that effect beyond certain distance. Okay, electric field due to a point charge is a spherically symmetric. So what is the meaning of that? Suppose we have a point charge, then the electric field will be formed in a surface of a sphere. So on the surface of this sphere, electric field will be constant. Suppose E1 is constant, E2, even though E1 and E2 are different, but E2 on entire surface will be still constant. Okay, so if you change the distance, electric field will change. But if you have a point like this, and if you draw a sphere, so a three-dimensional sphere is a circle, so that's why it looks like a circle, but it is a sphere because it has some surfaces inside and outside the board, right? Now let's discuss about electric field. When a positive charge is kept inside an external electric field, it experiences a force in the direction of the electric field, and a negative charge is kept, it experiences a force in the opposite direction of the electric field. So if you see that in certain cases the force is getting force in the direction of electric field, then this must be a positive charge, and if the force acting on the charge is in the opposite direction, then this must be a negative charge. Okay, now electric properties of electric field lines. Based on these simple properties also we have seen questions coming in KCET and Comet K. Field lines start from positive charges and end at negative charges. So starting point of electric field line is positive charge and it ends at negative charge. By the way, what is electric field lines? Electric field lines is the visual representation of electric field. Okay, so if you try to think electric field, basically electric field is invisible, right? So when you want to draw something and you want to show some electric field, then you have to draw some lines. Those lines are called electric field lines. That's it. Okay, it is not some rocket science, and it always start at positive charge, ends at negative charge. In certain cases it can start from infinity as well. For example, if you have only a negative charge, then in that case the electric field lines can start at infinity and it will end at negative charge. So either a positive charge or at infinity, electric field line starting point. So either infinity or a positive charge. Okay, and in a charge free region, electric field lines can be taken to be continuous curves without any breaks. So if there are no charges present, we can consider the electric field lines to be a continuous line, no breaks between the lines. But if there is some charges present, then there can be breaks present in the electric field lines. But if there is no charge, then electric field lines can be considered to be continuous curves. Next is a tangent drawn at any point on the electric field line gives the direction of electric field at that point. So suppose we have an electric field. Okay, we have an electric field lines, and if you this is the direction of electric field. I want to find the electric field particularly at this point. This is a curved line, right? So how to find the direction of electric field? If you draw a tangent at this point, that tangent represents the direction of electric field at this particular point. Okay, each and every point the electric field direction can be different. Okay, and that tangent basically gives the direction of electric field. two field lines can never intersect each other. If they did, the field of the at the point of intersection will no longer be unique, and which is not possible. So basically, what is the meaning of that? Two electric field lines, if they cross, suppose one is going in this direction, another one is in this direction. So at this point, if you can draw a tangent on this line, you can draw a tangent on this line as well. So if two electric field lines cross each other, then at the point of intersection you will have two different directions of electric field, which is not possible. That's why this is also not possible. So two field lines can never intersect each other. Now next is electrostatic field lines do not form any closed loop. Okay, so electrostatic field lines are open loops, so they can either start from positive and end at negative, or they can start at infinity, end at negative, or they can start at positive and go to infinity. Okay, but they will never form a closed loop. Closed loop means starting at positive, coming back at positive. If that happened, then we could have said electric field lines can be a closed loop, but that is not possible. So electric field lines always form open loops. Okay, electric field in free space decreases as we move in the direction of electric field. Suppose we have electric fields like this. Okay, so if you move in the direction of electric field, then the value here is high, and as you are moving in the direction of electric field will be decreasing. Okay, so if you move along the direction of the arrow, the electric field will slowly decrease. Okay, next is electric field due to a system of charges. System of charges means, suppose we have multiple charges Q1, Q2, Q3 and so on, and we are trying to find electric field at some point. So far whatever we have discussed is due to one single point charge. Now you have a system of charges. Okay, n number of charges are present, and you want to find the total electric field at this point. So how can you calculate the total electric field at any point? So the method is very simple. You have to find the individual electric field due to all the charges. Okay, so if they are positive, they will be outward. If they are negative, it will be towards it, and then you have to do a vector addition. Okay, that is the method of superposition principle. Not mathematically may not be important, but small short questions might come saying that the method that you use to find electric field due to a system of charges will be superposition principle, and it will be a vector addition. It will not be a scalar addition, it will be a vector addition. So you can write them as, this is the general formula. Total electric field is given by EI, I equals to 1 to n. I means I is a representation. I can be 1, I can be 2, I can be 3, I can be n as well. So E1 plus E2 plus E3 plus dot 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 plus En. So this is the sum sign. Sum means summation. So you are adding all of the individual electric fields in vector form. So it is a vector addition. Now let us solve a question. Three small spheres, each carrying a positive charge capital Q, are placed on the circumference of a circle of radius small r to form an equilateral triangle. The electric field intensity at the center of the circle will be. So let us draw the figure. First we have a circle. Okay, we have a circle, and we, on the circumference of this circle, we have three charges. Say this is charge number 1, this is charge number 2, say, and this is charge number 3. Now they are located such a way that the triangle, once you make it, it will be a equilateral triangle. Even though it does not look an equilateral triangle, these 2 points will be slightly above, but this will be an equilateral triangle. That means all the points are at equal distances. Now if you consider this is the center, okay, then this will be the radius r, this will also be the radius r, and that will also be the radius r. Okay, and because it's an equilateral triangle, by geometry you can show that these angles will be this angle and the angle between the forces will be all 120 degree. So basically you can draw, this is the center, and one force is acting in the downward direction, another force is acting in this direction, and the third force is acting on this direction due to this charge, right? So this is force number 1, this is force number 2, this is force number 3, and the angle between them is always 120 degree. So that total angle is 360 degrees, right? Now when three equal forces, why the forces are equal? Because all the charges are equal in magnitude, Q, 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 right? So we can say that E1 is basically E2 equals to E3. So all the forces are equal in magnitude. Direction is different, but magnitude wise all the forces are same, and that is K, capital Q, divided by R square. R is the radius of the circle. Now three equal forces, all of which are at an angle 120 degree, using Lami's theorem you can show that the resultant of these three forces is equals to 0. Okay, this is a very basic geometry. You can remember it, that three equal forces, when they are acting at an angle 120 degree with each other, the resultant is 0. Okay, so correct answer is option D. So this is a standard KCET style question. In standard KCET style questions, the answer, the question might be looking like a complicated problem, but the answer is basically simple. Now let's move on to the next question, next part, properties of electric field lines. We are already discussing it. So field lines start from positive, this is already discussed. So let's move forward. This is the properties of electric field lines, right? Field lines start from positive charges, end at negative charges. If there is a single charge, I think we have discussed it, right? These properties are discussed. Now let us go back to the electric dipole. So what is electric dipole? Two equal and opposite charges separated by a small distance is known as electric dipole. As simple as that. So two small charges means in the order of microcoulomb, nanocoulomb, they are considered to be small charges. Anything say coulomb is not a small charge, right? So anything in the small charge means microcoulomb, nanocoulomb, they can be considered as small charges. And if the distance is small, means it can be a nanometer or micrometer. So the distance is also very small. In that case, these two, Q is small and the distance is small, then this is called an electric dipole. Generally the distance between the dipole is denoted by 2a. So this 2 is not a separate factor. Remember that 2a itself is the distance. So if you see in some cases the distance is given, do not multiply with an extra 2. This 2 itself is the distance, because whenever we are applying some formulas, some equations, it helps to know the value of a. So basically half length. Okay, but in the question sometimes the half length will not be given directly, 2a, that is the total distance, will be given. So be careful and do not confuse with 2a with a. Okay, a is half length, 2a is the total length. And generally one example of this is hydrochloric acid, HCl. So if you consider hydrochloric acid, the hydrogen is slightly, so the electron pair which is being shared between hydrogen and chlorine, because of higher electron affinity of chlorine, that electron pair slightly shifted towards the chlorine. Now because it's a molecule, okay, their bond length is very, very small, okay, and because they are shifted, the chlorine becomes slightly negative, the hydrogen becomes slightly positive. So you can consider it to be a electric dipole. Now let's move on. Dipole moment, the most important concept of this part. So electric dipole moment is the product of magnitude of one of the charges and the distance between them. It's a vector quantity. So if you consider minus charge and plus charge, if you take any one of the charge, that is Q, and if you take the total distance between them, that is 2a, then this is called dipole moment, and in vector form there is a n cap. What is n cap? N cap is the unit vector from negative charge to positive charge, so that represents the direction of the dipole moment. So dipole moment, direction of the dipole moment. Dipole generally does not have any direction, but dipole moment has. So from negative to positive, this is the direction of n cap. It's an unit vector. Okay, basically gives the direction. So dipole moment is a vector quantity pointing from negative to positive. The unit of dipole moment is coulomb meter, and its dimension is L into A into T. Okay, lat. Okay, lat you can remember, L is for length, A is for current, and T is for time. 3-point charges plus 2q and minus 4q are placed at the corners ABC of an equilateral triangle ABC of side X. The magnitude of the electric dipole moment of this system is. So here we have an equilateral triangle. Okay, so this point has charge, say plus 2q, this one has a charge plus 2q, and this one has a charge minus 4q. You have to find the total dipole moment. Now first of all, this is a equilateral triangle. Equilateral triangle sides, we are not interested super on side. We just need this angle. So in an equilateral triangle, all the angles are 60 degrees. So this is what we needed. Now how to solve this question? So what we will be doing, we will be doing a small trick, that we will take this minus 4q and we will divide it into two charges. One is minus 2q, another one is another minus 2q. Okay, so minus 2q, so that total charge remains minus 4q. Now we will consider this plus 2q and this minus 2q. We can consider this to be a dipole. Similarly, this can be also considered as a dipole. So basically we have two dipoles, and both dipole moments are from negative to positive, so in this direction, and this is also negative to positive in this direction. So one dipole moment in this direction, one dipole moment in this direction. So two dipole moments, the angle between them is 60 degrees. We have to add them. Both dipole moments have the same magnitude, because if you see any one of the combination, plus 2q minus 2q, minus 2q plus 2q, so the magnitude is same. So what is the dipole moment? By the way, the distance is given x. So dipole moment is given by any charge, magnitude of any charge times the distance, which is x. So 2qx is the dipole moment of any one of these dipoles. Right? Now what is the vector sum of these two vectors? So vector sum is given by the net dipole moment, can be written as square root of a square plus b square plus 2ab cos theta. Right? This is the basic formula of vector addition. Here instead of a and b, we have both of them as p. So now simplify. So 2p square plus p square 2p square plus p into p is p square, so 2p square cos 60 degrees. Now what you can take? We can take this 2p as common, so we can write 2p square 1 plus cos 60. Now what is cos 60? Cos 60 is half. Cos 60 is half. Okay, you can remember it. Cos 0 is 1, cos 90 is 0, cos 60 is half. So it will be square root of 2p square into 3 by 2. 1 plus half is 3 by 2. This 2 cancels. So you can write this as root 3 into p. Okay, or root 3 into 2qx. So this 2 is constant, so I am writing 2 first, into q into x. So 2 root 3 qx is the correct answer. Option A is the correct answer. Simple question, not tumba difficult, but if you know how to approach this question, you can solve it. If you don't know, you will not be able to solve this kind of question. Even though it's easy, considered easy question, but the method, knowing the method is very, very important. Now there are two cases that you have to remember. These are the basic formulas. Derivations is part of PU board, but not obviously not for KCET or Comet K. The field due to an electric dipole for point on the axis is given by E axial. E axial equals to 1 by 4 pi epsilon naught 2p by r cube. Okay, and for points on the equatorial plane, this is called equatorial plane, the electric field is given by minus 1 by 4 pi epsilon naught p by r cube. Ideally there should be a vector sign, as you are using a negative sign. Okay, now this negative sign represents that the electric field due to these charges, if the suppose this is the positive charge, this is a negative charge. So the dipole moment will be from negative to positive. The electric field will be in the opposite direction. So basically this negative sign indicates that electric field on the equatorial plane is basically in the opposite direction of the dipole moment. That's it. Okay, the negative sign represents the equatorial plane. Electric field on the equatorial plane is on the opposite side of the dipole moment. If you consider these two on the same line, then the direction is opposite to each other. Okay, now dipole on an uniform axis in an external field. So now we have a dipole. Okay, say this is positive, this is negative. Now we kept it in an external electric field E. Okay, in that case, when you keep the dipole in an external electric field, okay, there is a torque which will act on the dipole. So the torque acting on a dipole kept in an external electric field is given by tau equals to P cross E, or tau equals to PE sin theta. In uniform electric field, net force is 0, but torque is not 0. So if the electric field is uniform, that is constant throughout, then there will be only torque, no force. Okay, but if the electric field is not uniform, then both force and torque are non-zero. The torque is 0 when theta equals to 0 or 180 degree. So for uniform field, force is 0, torque is not 0. In non-uniform field, both force and torque are not 0. Nothing is 0. But the torque can be 0 at some specific points for both cases. Okay, when theta is 0 or 180 degree, in those two cases sin theta becomes 0, so that's why torque becomes 0. Now electric flux. Now we are going into the last topic of this electric flux and then Gauss's law. So a liquid flowing with a velocity v through a small flat surface, say ds or delta s, in a direction normal to the surface, the rate of flow of the liquid is given by the volume crossing the area. So suppose we have a pipe. Through the pipe some water is coming out. Okay, I want to measure the volume of water which is coming out of this pipe. So how to do that? We have to find the cross-sectional area and the velocity of the water. If you multiply these two terms, you will get the total volume of water which is coming out of this pipe. Basic mathematics, right? So so basically VDS represents the flux liquid flowing through the cross of the plane. Now in some cases the liquid might flow in a separate direction and cross-sectional area can be a separate direction. In that case you have to consider the component of the velocity in this direction, and then you have to take the cos theta component. Okay, so this is for liquids. Okay, liquid flowing through a pipe, in that case we using this, and this is called flux. Okay, this quantity is called flux, the volume. Basically flux represents the volume. Flux is basically volume of fluid coming in 1 second. Okay, in case the angle is, as I said, is not 90 degrees, in that case delta S and V are in the same direction, but in this case delta S and V are not in the same direction. V is in this direction, delta S in some other direction, then flux is basically V into delta S cos theta. You have to consider the angle cos theta. Okay, clear? Now let's move on. For the case of the electric field, we define an analogous quantity called it electric flux. So electric field, even though it is not like water, it is not flowing basically, but still for electric field, we can consider something analogous. Analogous means which is similar, okay, which is similar to that of liquid flowing through a pipe, okay, and that quantity is called electric flux. Now what is electric flux? Let's understand. Suppose electric field lines, instead of water was flowing, here we consider electric field lines passing through a surface area. Okay, so if you take a surface area, say delta S, and the electric field of strength capital E, then the electric flux is E into delta S. So E can be considered as the speed or velocity of the electric field, and delta S is the area. So electric flux is basically given by E into delta S. But what if the surface area does not make 90-degree angle with the electric field? In that case, you have to consider the angle theta, and it again gives you E delta S or E dot ds. Okay, E dot ds, because cos theta is basically dot product. So this is a representation of electric flux. Electric flux is a scalar quantity, because it's a dot product of electric field and area vector. So definitely it's a scalar quantity. Now let's move on. So now we will discuss about three different charge densities. So there are three different charge densities. Line charge density represented by symbol lambda. Its unit is coulomb per meter, and dimension is L to the power of -1 A T. Don't worry, you will get the entire PDF. So download the PDF and follow these things. These are very, very important. Surface charge density sigma, unit is coulomb per meter square, and its dimension is L to the power of -2 A into T. Volume charge density rho is given by coulomb per meter cube, L to the power of -3 A into T. Okay. Now, Gauss's law, another very important concept. Gauss's law states about electric flux, the electric flux that we have learned. So electric flux through a closed surface S is given by sigma equals to Q by epsilon naught, or E dot ds equals to Q by epsilon naught. Here Q is the total charge enclosed by surface S. In the KCET PUC, you solve some question based on Gauss's law. So basically it talks about the electric flux if you have a closed surface. Closed surface means, as I mentioned, the doors of your classrooms are closed, no one can escape, then that is called a closed surface, and Gauss's law is valid for any closed surface. Now in the case of Gauss's law, whatever charges are inside, no matter where they are located, if you add all the charges, you get the total charge Q. Sometimes it is also represented by QEN. EN means enclosed. Okay, so the total charge enclosed in this volume, and if the flux which is coming out of this surface, say phi, total flux, okay, including all the surfaces, total flux coming out of this is phi, then phi can be calculated by Q dot epsilon naught. Now phi we know is basically E dot ds, and if you do the integration, you get the total flux for all the surfaces. E dot ds basically means, suppose electric field at this point is E and ds is this, okay, then E dot ds basically gives you the electric flux out through this small area. Now if you want to calculate the entire surface area, you have to do the integration. Okay, Q is total charge enclosed by S. Now few points you have to remember about Gauss's law. Each points are important. Maybe it can be a statement based question, maybe it's a true false based question, which one of them are wrong, which one of them is correct. So this type of questions are very common from Gauss's law, so you have to understand it carefully. Gauss's law is true for any closed surface, no matter whatever is its shape and size. Okay, so based on this also we have seen questions. So Gauss's law is valid only for spherical surfaces, only for square surfaces. No, it is valid for all surfaces as long as the surface is closed. Okay, so as long as the surface is closed, Gauss's law is valid. Here Q includes the sum of all the charges enclosed by the surface, the charges may be located anywhere inside the surface. It can be near to the surface, it can be just inside, it can be at the center, does not matter. No matter wherever the charge is located, Gauss's law is valid, and the charge Q represents sum of all the charges. Anything outside is not considerable, but anything inside will always consider. Electric field is due to all the charges, but Q is only for inside the surface. The electric field E dot ds, that electric field is, maybe some charges are located outside. Suppose we have a surface, some charges are located inside, some charges are located outside. So when you are talking about electric field E, this electric field E is due to this charge and this charge. Okay, so be careful. The electric field is due to all the charges, but the electric flux is only for the charges which is inside. So this is a very big difference. The surface that we choose for the application of Gauss's law is called Gaussian surface. Gauss's law is often useful to calculate the electric field due to for symmetric surfaces. Symmetric surfaces means sphere, okay, plane, square, or in a cylinder. They are symmetric surfaces. So in those cases, Gauss's law can be very, very useful. So here are the applications of Gauss's law. So first we have applied Gauss's law due to an infinitely long straight uniformly charged wire of surface charge density lambda. The electric field is given by, this is a way to remember, 1 by 4 pi epsilon naught 2 lambda by r. Some people are familiar with this 1 by 2 pi epsilon naught lambda by r. So whatever you are personally comfortable, you can use that. I personally am comfortable with this expression because 1 by 4 pi epsilon naught, sometimes if you are solving a problem, this can be written as 9 into 10 to the power of 9, so you don't need to change anything. That's why I prefer this formula. If you are familiar with this formula, that is also okay, but you have to remember that electric field for a infinitely straight long wire is inversely proportional with distance, not with the square. Generally electric field is proportional to 1 by r square, right? In this case electric field is proportional to 1 by r only, and lambda is the surface charge density. Okay. So no matter what is the total charge on the wire, it only depends on the surface charge, line charge density. Field due to an uniformly charged infinitely plane sheet. So here we have a uniformly charged plane sheet, non-conducting sheet. Okay, the electric field is given by sigma by 2 epsilon naught. So electric field is given by sigma by 2 epsilon naught. Sigma is the surface charge density. Sigma is the surface charge density. So unit surface area, whatever is the charge. Okay, so this is a constant, as you can see. So due to a infinitely long charge sheet, electric field anywhere is constant. Okay, next is electric field due to a spherical shell. So spherical shell, outside the spherical shell, the electric field is dependent on 1 by 4 pi epsilon naught q by r square, whereas inside the shell it is 0. Inside the shell electric field is 0, outside the shell it is inversely proportional to 1 by r square. So E equals to 1 by 4 pi epsilon naught q by r square. Now let's solve one interesting question which might seems very easy, but actually it's not. Let's see. Consider a thin spherical shell of radius capital R consisting of uniform surface charge density S. The electric field at a point of distance capital X from its center and outside the shell is. So we have a shell, we have a point at a distance x which is outside. So what is the electric field at this point? So electric field at this point is 1 by 4 pi epsilon naught q by x square. Now this is simple. Even though I said this is a difficult question, it is a simple question. Only thing they have mentioned that surface charge density is S instead of Q. So you can write 1 by 4 pi epsilon naught. Instead of Q you can write surface charge means surface area 4 pi r square into surface charge density. So total charge of an object is given by, suppose it's a surface charge density, total surface area times the surface charge density. So mass of an object is density times its volume. Similarly, total charge is given by surface area times the charge density. Right? Now this is x square. So electric field is directly proportional to surface charge density. Electric field is inversely proportional to square of the distance. So these are the 2 points. So inversely proportional to S. Is it inversely proportional to S? No. So this is wrong. Directly proportional to x square. Is it directly proportional? No. This is also wrong. Directly proportional to R. Yes, is it directly proportional to R? If you consider the proportionality with radius, you will see it is directly proportional to R square. So this is also incorrect. Okay, inversely proportional to x square. Is it inversely proportional to x square? Yes, it is inversely proportional to x square. So this is also correct statement. So this is the correct statement. Remaining 3 are incorrect.